In this quick video, I'm going to try to fix two dead ESP32 boards and also show how to use serial communication between a Raspberry Pi and an ESP32. After my last tutorial where I recovered a brick BIOS, I got a lot of positive feedback encouraging me to make more repair videos. The other night my Lowland 32 Pro died, so I figured the troubleshooting might be of interest. The Lowland 32 Pro is an inexpensive ESP32 board that comes with 4 MB of flash and PS RAM, a battery charging circuit, and an SD card slot. Unfortunately, they seem to have a high failure rate based on comments on the MicroPython forum. In addition to the Lowland, I also need to fix the generic ESP32 that broke during my MQTT tutorial. The Wemos Lowland 32 is plugged into a Raspberry Pi via USB. The USB cable provides power and communications. On the Pi, in a blank terminal, type dmessage grep tty USB. The Pi sees the board on tty USB 0, but when I run R shell, the command hangs at connecting. Eventually it throws a Pi board error. Just to make sure it's not a Raspberry Pi issue, I'll plug the ESP32 board into a PC. Windows throws a USB device not recognized error. This suggests a problem with the USB to UART bridge. I inspected the board. The micro USB jack looks okay. I didn't see any cold solder joints or other obvious damage. The first repair step after a visual check is to measure voltages. Sometimes poor quality USB cables or power supplies cause undervoltage issues. The ESP32 5V rail is at 4.9 volts, which is a little low but within tolerances. The Pi's 5V rail is also just under 5 volts, so there's not much voltage drop through the USB jack or cable. Switching to the ESP32's 3.3 volt rail shows 3.23 volts, which indicates the step-down regulator is okay. A failed CP2104 USB to UART bridge would explain the connectivity issues. The chip's right next to the reset button, which gets pressed frequently, making it susceptible to ESD. Despite the USB not working, it's still possible to check the ESP32 module using a serial connection, which is very easy to wire. The Pi's RX pin GPIO15 is connected to the ESP32's TX pin. The Pi's TX pin GPIO14 is connected to the ESP32's RX pin. It's also necessary to provide power. A 5V pin on the Pi is connected to the ESP32's V-in, and the grounds are connected. Always be careful with 5V lines because the GPIO pins can only tolerate around 3.3 volts and are susceptible to damage at higher voltages. On a breadboard next to an old Raspberry Pi B+ is the faulty Lowland 32 Pro. I'm using an older Pi because some newer Pis reserve the primary high-throughput full-featured serial port for Bluetooth. There are workarounds, but this is easier. I'll include more details on my website. The Pi's RX pin is connected to the ESP32's TX pin. The Pi's TX pin is connected to the ESP32's RX pin. A ground pin on the Pi is connected to a ground pin on the ESP32. A 5V pin on the Pi is connected to the V-in pin. I recommend you make all connections before powering on the Pi. Okay, that's all it takes for the wiring. On the Raspberry Pi, open a blank terminal. Type dmessage grep tty-ama. tty-ama 0 is found. However, it's being reserved by the console, which is enabled and will cause problems. R shell tacp dev tty-ama 0 should fail, and it does. To remedy, click the Pi's main menu, click Preferences, click Raspberry Pi Configuration, click the Interfaces tab. The serial port is enabled, which is correct, but the serial console needs to be disabled. Click Disable and Yes to reboot, which is required. After rebooting R shell tacp dev tty-ama 0, now the connection works, which means the ESP32 module is probably okay. ls/piboard/flash shows my files are still there, so the flash is probably okay. REPL enters the REPL, import machine, reset, resets the ESP32. The boot up looks normal, and the Wi-Fi connection is successful. All good news. I'm pretty sure the problem is the CP2104 chip. In the past I've relied on an iron to do surface mount soldering, however the CP2104 is a 24-pin QFN, which stands for Quad Flat No Leads Package. These are challenging to repair using only an iron, so I went ahead and ordered an 858D+ hot air rework station. It's got adjustable airflow and temperature, a digital LED temperature readout, it doesn't take up much desktop space, it was only $42 US, which is a fraction of what a decent hot air station costs. The 858D is sold by many vendors, and it's hard to tell what you're going to get inside in terms of PCB, microcontroller, and components, but most of the shortcomings have been addressed by hackers. There are schematics, add-ons, adapter boards to swap out the MCU, and improved firmware is available. I also went ahead and ordered a replacement CP2104. It only cost $1 and change with shipping. When I got home today, I found a rather large box on my doorstep containing this long ESD bag, the contents being this chip tube, which contains a single CP2104. I appreciate all the ESD protection, but not the most efficient packaging. The chip is only 4 millimeters square. Before I remove the old chip, it's important to note the pin 1 orientation, which is indicated by the little dot in the corner. The 858D is my first hot air station. This little chip may have not been the best choice to break it in. By the way, there are many great hot air rework tutorials on YouTube. This video is not meant to be a how-to reflow. Depending on the results, it might become a how not to. I covered some of the board with Kapton tape so I don't melt any of the plastic parts and to reduce the chance of inadvertently blowing a small passive off. I have the air gun set at 300 degrees Celsius. I don't know if it's accurate because I can't find the thermocouple for my multimeter. I have the airflow set in the middle. The tip is a little large for this small chip. It's a little hard for me to see what I'm doing because the camera's in the way. Well, that works surprisingly well. The video is not sped up at all. The chip came right off with no damage to the pads and nothing else got disturbed. Soldering braid is used to clean up the solder residue. The tiny pads are fragile, so I like to drag my iron along the long axis of the pads as opposed to dragging across them. After the braid, I'll use superwash to clean up any dirt or flux. A good clean surface always makes for better soldering. Also make sure the PCB is dry so moisture doesn't outgas through the solder paste. Next, solder paste is applied to the pads. This cheap plastic applicator is pretty clumsy. It's very difficult to control the volume. A solder mask would be preferable. I'm applying too much solder paste, but I'd rather err on the sufficient side because I'm pretty sure I can remove the excess with my iron. This seems like the hardest part. I guess there's an art to it. A smaller tip would also help. Okay, I bodged that up, but I think it'll still work. ESD tweezers are used to place the chip. Again, make sure the orientation is correct. The placement doesn't have to be perfect because once heated the surface tension should afford minor corrections. Just make sure you're not off by too much. That looks close enough. I'm using the same temperature and flow settings as before. Ideally, you would try to moderate the temperature to match the reflow profile specified for the chip. This could be done by adjusting the height of the gun. I'm just winging it. Okay, I see some capillary action, and the chip looks set. There are a couple bridges, but nothing I can't fix with an iron. I turn the chip around in the vise to get better access to the two sides with solder bridges. Sorry about the camera angle. I'm just carefully brushing my iron over the bridge pins to scoop up the excess solder, cleaning the tip between brushes. Despite my sloppy reflow, all the pins look okay. Another cleaning, and it should be ready to test. Here's the moment of truth. I'll plug in the USB. No magic smoke, which is a good sign. The LOLAN32 doesn't have a power-on LED, so it'll only need to be checked with software. I switched to a Raspberry Pi 3 because it's a lot faster than the old B+. D-message grep TTY USB. The CP2104 is recognized. RShell TAC P dev TTY USB 0. Connecting. Alright, it's working. ls/piboard/flash. My files are still there. REPL. Looks like everything's good to go. Next is the generic ESP32, which I just swapped out for the LOLAN32 Pro. D-message grep TTY USB 0 shows nothing. This one probably just needs a new micro USB jack because it was intermittently failing. I inspected the jack and it has physical damage. It's barely holding the plug in and it's not straight. I'll patch the V-in pin on the ESP32 to a 5V pin on the Pi. The LED indicates that the board is now powered on. The USB cable is obviously providing a ground, but I'll add a ground patch just for good measure. I'll skip the serial test because I think it might work now. D-message grep TTY USB 0. Now the CP2104 is recognized. RShell TAC P TTY USB 0. The connection is successful. ls/piboard/flash shows the files on the ESP32. REPL. All's good, just needs a new jack. The board's mounted in the vise with some Kapton tape. The heating will take a little longer because the jack's metal shell acts as a heat sink. There it goes. A desoldering iron is used to clean out the through holes. Off camera I used solder braid and cleaned the pads. The big through hole pads are a lot easier to apply the solder paste. Again, I'm applying way too much to the small surface mount pads. Off camera I removed a good micro USB jack from a fried Raspberry Pi that was beyond repair. The jack's back through-hole pins line up correctly, but unfortunately the front pins are off, so I just bent them at 90-degree angles and I'll surface mount solder them. Okay, the solder's melting. Looks like I got one solder bridge on the data pins. Nothing that a little solder braid can't fix. I'll need some more practice with the hot air gun, but the jack looks good enough. Back on the breadboard, I'll plug in the USB cable. Now it's got a tight fit and the LED power is on. I think it's fixed. ESP tool TAC P dev TTY USB 0, flash ID. The ESP32 chip is detected. The flash size is correct. R shell TAC P dev TTY USB 0. And we're connected. And the Rebel's working too. I hope you found this video interesting. You can support this channel by subscribing, leaving a like, and sharing. Thanks for watching.